Today we have Professor Pierre Baldi from the Computer Science Department at the University of California, Irvine, who's going to talk to us about attention in deep learning and physics applications.
Thank you, Peter. So first, let me briefly mention a book that I've written that is coming out with Cambridge University Press, which has a whole chapter on applications to physics. You can find the table of contents and sample chapters on my website if you are interested. So attention, let me mention a few high-level basic facts, and then we'll go into the details. But if you look at deep learning today, deep learning architectures, etc., you will see that attention is mentioned very often, and it's widely used in modern deep learning. I will try to convince you that attention is not something new. It's just the rebranding of a classical notion, the notion of gating, in the same way that deep learning is a rebranding of a neural networks. But it's not because it's an old idea that it's not useful. Attention is a very useful idea. It expands the repertoire of differentiable operations available in neural networks. Differentiable is important because you want to learn by gradient descent, of course. And therefore, it also expands the repertoire of functions that can be implemented in an efficient way by given architecture. Efficient is the key word here. And the basic idea, it allows modulation of the input-output function response of a network to be modulated by another network, an attention layer, or a series of attention layers, etc., so that your basic network is able to compute different functions as a function of this modulation. That's a basic idea. So let's, you're physicists, you like fundamental principles, so let's try to go down to the quarks of attention, the fundamental building blocks. So you know that the fundamental McCulloch and Pitts model for neurons in neural networks is the one that you see on this slide, where a neuron is a computing device that has a number of synaptic weights. And the way it computes things, it receives an input signal X, and it does two basic operations. It takes the dot product of the input X with the synaptic weights to produce this weighted average sum, which is called the activation. And then it transforms the activation into an output via a so-called activation or transfer function F, which can be the identity in the most simple case. Then you have a linear neuron, or more often it's a nonlinear function, and you have a whole repertoire of such functions that are routinely used. Things like Heaviside sort of threshold functions, sigmoidal functions from tan-H to the logistic sigmoidal function, or other ReLU, piecewise linear, etc., right? So that's the basic model. And we know that it has universal approximation properties in the sense that the network made of such little computing units can approximate any function. So in a sense, there is no need to make this model more complex because it can already do anything you want in some sense. But of course, you may want to make it, explore ways of making these neurons a little bit more complex, because that may lead to more efficient or compact architectures or more efficient learning for particular tasks. So what are some of the directions you can explore to make these neurons a little bit more complex? A classical one is to make the activation function a little bit more complex. Instead of being a linear function, you can make it quadratic, or more generally, a polynomial of degree d, right? So in this case, the activation here is a quadratic function or cubic function, let's say, of the inputs. And then you still have your nonlinear activation function and you produce the output, right? So the complexity now occurs in this activation. And what you have now is the ability of taking terms which combine different input, xi, xj, take their product and multiply them by a two-way synaptic weight, if you want. So you get a more powerful neuron, but of course you pay a price. That is, you need now n square parameters because you have n square synaptic weights of the form Wij, right? And so everything is about this trade-off of complexity, the cost in terms of parameters and what you gain in terms of expression power. And you see here that the trade-off is expensive. The number of parameter is n squared. And attention is a little bit a way of doing a little bit of that without paying the n squared price. And it goes back to the idea of gating. So let me go back again, quarks of attention. This is the slide that tells you really what is the basic thing that is going on. You can do output gating, which is shown here on the left, where you have a neuron I that produces its standard output OI, but then it's gated by a neuron J. And what happens is that the two outputs get multiplied with each other. So that effectively neuron I now is producing OI times OJ as its output, and it's broadcasting it along all its outgoing connection, so that a neuron K downstreams receives from this neuron I an input that looks like this. So there you see the quadratic expression begins to appear. So that's one form of gating, and that's the one that we're going to use. But there is also a slightly different form of gating where you do synaptic gating, where you have a neuron I connected to K by a synapse WKI. And again, neuron J is gating now the synapse where you get a new synaptic weights equal to this product. And when you reach neuron K, it's the same thing. There is no difference. The difference between these two mechanisms is this is very precise in terms of geography. You're just gating this connection, whereas here you're you're gating all the outputs of neuron I, and these get broadcasted over all the connections that are coming out of neuron I. Of course, if there is only one connection coming out of I, the two mechanisms are equivalent. And this is actually what happens in the attention mechanism that you see in most networks. So for the purpose of this talk, I'm just going to use output gating. But again, remember that if you have a single outgoing connection from neuron I, it's the same thing as synaptic gating. So I claim that all the attention networks that you see are just based on this mechanism, just amplified and used many times in many layers, etc. But this is what is really at the root of attention, is just the concept of gating, introducing a new operation in the McCulloch and Pitts model where you can multiply the output of neurons. Multiplication is differentiable, so there's going to be no problem with backpropagation. It's also symmetric, although from the topology of the network, it really makes sense to say that J is gating I and not the other way around, because OI/OJ ends up being transmitted on the connections emanating from I and not from the connections emanating from J. So it's not a symmetric operation. So this is the expanded McCulloch and Pitts model where we still stay with linear activation So we have a dot product of X with W. We don't use all quadratic terms at that level. We have nonlinear, linear or nonlinear transfer functions, but then we allow for the product of neuronal outputs. Now, what happens when you do that? What do you gain and what is the cost? That is going to be the essential question. So let's look at the effect on the, if you want, on the transfer function. So imagine that you have gating neurons with different activation functions, such as a gating neuron that has a linear activation function, a heaviside 0,1 heaviside function, a sine threshold function from -1 to 1, or a ReLU. And imagine that this neuron is gating another neuron which has similar transfer functions. And imagine that they have the same inputs. What happens? Well, if you're gating linear with linear, you're multiplying the two linear functions, you get a quadratic function. But notice that instead of having n square parameters for all possible term x, y, yj, you only have a linear number of terms, right? Because here you have sum of ai xi, here you have sum of bi xi. When you take the product, you only have n parameters here and here. So you have two n parameters, and you get quadratic terms. Not all of them, but a certain number of them. So you can see again, this is a way of introducing quadratic terms without using n-square parameters. If you gauge a ReLU function, a linear function by a Heaviside function, you get a ReLU function. So that's one way of seeing that ReLU are interesting functions because they come out immediately from this process. ReLU gating itself is also gives you a ReLU. So you see there is a lot of ReLU on this table. And you get a few other things, the wedge function, which is also recently has been shown to have interesting properties. It leads to more robustness against adversarial attacks, for instance, etc. So that's one first way of looking at the effect of attention at the level of single neurons. Another way of looking at it is to look at what can be done with attention that could not be done before. And the classical example is the XOR Boolean function, exclusive OR. You should know, and it's very easy to prove, that a single neuron, a linear threshold gate, let's say, cannot compute XOR. You need at least one hidden layer. And with one hidden layer, you can easily compute XOR. Now imagine that you allow attention, so you allow the product of the outputs. I claim you can compute XOR without hidden layer immediately. So the way you do that is you first have a neuron that computes the OR function. That's very easy to do with a linear threshold gate. You compute the OR function. And then you have a gating neuron that computes the NAND function. That's also very useful to do with a linear threshold gate. It's very easy to prove that. And now, of course, if you take the product, you're taking the product of the last columns, you get this, which is the XOR. So a threshold neuron gating another threshold neuron gives you immediately the possibility of having XOR at the output without incurring the price of a hidden layer, okay? So again, it's not about whether you can do something with attention that you cannot do without attention, because you can do XOR without attention, you just need extra layers. So it's all about doing things in a convenient, compact, efficient way, right? Now you want to do things a little bit more sophisticated mathematically. What you can do is to look at all possible Boolean function of n variables and look at different subclasses. And for any class of Boolean function, I can define its capacity to be the log base 2 of the number of functions in that class. So it's the number of bits that you need to specify a function in that class. If you look at all possible Boolean functions of n variables, there is 2 to the 2 to the n, and so the capacity is 2 to the n. It's exponential. So next interesting question, you can say, well, let's look at all linear threshold function. So all the Boolean functions that can be implemented by a hyperplane that are linearly separable, and ask how many of those there are. So imagine taking the hypercube of all points that have coordinates 0 and 1 or -1 and 1. You color them randomly with blue and red, and then you're asking, is the coloring linearly separable? Is there a hyperplane that separates the blue points from the red points? Your intuition should be that, you know, for a random coloring in general, you will not get such a hyperplane, and that is correct. And the number of linear threshold function, or the number of colorings that is linearly separable, turns out to be 2 to the n squared, roughly. And so the capacity is n squared, which is what you see in this box. The capacity of linear threshold function is n squared as compared to the exponential 2 to the n for all possible Boolean function. This is a result that was originally proved by Zguev in the late 1980s. Not a very well-known result, but one of the most fundamental results of neural networks, I would say. So now you can say, with attention, how much do I increase that number, right? So if I have a linear threshold unit that is gating another linear threshold unit, what is the number of new functions that I can compute? And I'm not going to go through the details, but you can prove that it's 2n squared. So you are doubling the capacity, but you're also doubling the number of parameters, because now you have 2 threshold neurons. So it's, in a sense, it makes sense. You double the number of parameters, but you also double the capacity. And it's all about, are there interesting functions that lie in this expanded box that has capacity, double the capacity, that are useful for particular problems. The way you show things like this theorem about 2n squared is basically you take intuitively, you take a linear threshold function, so it looks something like this. You take another linear threshold function randomly. If you take random linear threshold function, the two hyperplanes would be essentially orthogonal. And then when you take the product, you're going to get this arrangement, and you can see the arrangement is non-linearly separable. So basically, if you take two linear threshold functions and you combine them together by attention, you get something that is not a linear threshold function, you get a new function. And so the capacity, which are the logarithms, add together. And so you get n squared plus n squared equal to 1 squared. All right. This was all at the level of single neurons. Let's go scale it up and let's go at the level of layers. What can you do with layers of neurons if you allow this gating, this multiplication? Well, the big thing you can do is you can take dot products now. So if I have a network that somewhere is producing some output x1, x2, xn, and I have a gating neuron that produces v1, v2, vn, I can allow v1 to gate x1, v2 to gate x2, etc. So I get all the pairwise products first, and then I feed them on connections that are frozen to 1, not adaptive, these connections. And I have a linear neuron here, which finally computes the dot product. So suddenly I'm able to, if I am allowing this attention mechanism, I am able to compute dot products of vectors, something that you could not do, instantaneously in a McCulloch and Pitt network. And it's not instantaneous here too, because you have to do this attention, you have to have this extra level where you compute the sum of xi di, but today in modern code, this becomes a whole block by itself. It's sort of called an attention block where you're computing this dot product. And of course, dot products between vectors can be viewed as a similarity, right? Especially if the vectors have the same norm, which happens all the time in neural networks. You're now able to compare in a compact way two vectors and measure their similarity within your neural architecture. So you can think that this is a useful operation. The other thing you can do is to combine this with a softmax. So here I have a network which again has x1, x2, xn in one of its layers. I have y1, y2, yn coming up through the gating network. I transform the y1, y2, yn into a softmax. So now I have v1, v2, vn are normalized. They're all positive. They add up to 1. And now I apply them multiplicatively to the x1, x2, xn. So I get the weighted combination of the x1, x2, xn, which is convex because v1, v2, vn are convex weight. They come out of the softmax, right? So now you can do convex combination of outputs. And that too now is part of a single block, if you want, where you combine these dot product with these softmaxes to modulate the activities, the axes in the primary neural network. So that's an example. Of course, as the activity in the gating layer varies, these weights will vary, and so they will modulate what goes through the primary network, right? In this case, you have 08, 01, 01. On a different example, in a different situation, you may have 07, 02, 01, etc. Right? So that's the modulation aspect of the attention mechanism. This is not the only way of doing modulation. There are other ways. There is something called the parameterized networks that have actually been developed using physics. This is work with Daniel Whitestone and Kyle Kramer, where, for instance, you have a network that is looking at standard inputs, maybe jets, whatever, and you can add another input, an extra input, in this case, the mass, for instance, and you get an output, some classification, for instance. And the mass is available during training. So during training, you can just put it, you use it, but it's not available at test time, right? You could have You could have data where you don't know what the mass of the underlying particle is, but you can still use this network at test time by sampling different masses, for instance, or looking at the average or looking at masses in a particular range, etc. Right? So that's a parameterized network. Attention is another way of modulating what the network does I think in a more powerful way, because you can use attention at different layers in different ways, etc. Of course, with many more parameters in general. All this excitement about attention, which, as I've told you, it's basically gating, just to rebrand it, comes from actually natural language processing over the last 5 years or so. And the way it comes about in natural language processing is illustrated here, where you have an English sentence in the input. I took this on the internet. It's not a very good translation, actually, but whatever. The idea is that when you are translating a word in a sentence, and you're looking at the corresponding word in the target language, what matters for a particular word in the target language depends on the input, but in a different way. So when you're translating how into comment, what is most important to translate comment is the word how, and maybe was is a little bit important, and then your and they are not important at all. So you see it translated. Imagine these are softmax weights in these squares. So you can see that the softmax, the weights are different for each word, and usually they are sort of, there is a big weight that corresponds to the corresponding location in the sentence, but then there is some context around, and this can vary. You can imagine across different sentences, different languages, how the breadth and the configuration of the context could vary. So that's where attention was applied. And it has been very successful in natural language processing. And the best natural language processing you see today that you use all the time in your various applications are using these attention mechanisms in a massive way. Again, over the past few years, there have been different approaches to attentions, but they all boil down to this gating mechanism. And today, these attention functions, if you want, or blocks, have become standard in the usual software libraries, in TensorFlow, in PyTorch, etc. And they are available to you in very, very easy, very usable way. And the main sort of the pinnacle of attention networks today are the so-called transformer architectures that are used especially in natural language processing, and which have led to some of the best current state of the art in natural language processing. They are available in these libraries, and I'm going to argue that some of them are actually very useful. These functions are very useful for physics application. And I'll explain why and give you a couple of examples later in the talk. So if you look at a transformer, you try to read the transformer papers, it looks very, very complicated, and you don't see the main message that I'm trying to tell you, that it's all about gating. It all boils down to gating. So you will see diagrams like this, you will see expression like this one, etc., etc. And they have multiple levels of attention, both in the encoder part of the network. There is a decoder part, again, with multi-layers of attention. So if you try to draw a full transformer model as a neural network, it's a complete mess. In fact, no one has been able to do that because there is too many connections, too many wires. So I'm going to unpack it to you and make it very simple by showing you what happens inside one of the encoder modules. So the transformer has a stack of encoder modules. It has a stack of decoder modules. And I'm showing you one encoder module only, but they're all the same in terms of structure. And the decoder modules are very similar to the encoder. So if you understand this, you can then very easily start understanding the transformer papers. So imagine an encoder module is represented here. In the input, let's say these are words of a sentence that have been transformed into vectors by something like word2vec or something more sophisticated. But basically, you have a vector inputs here, and you have a sequence of such vectors. And you have a first network here that is shared at every position, the blue arrows, that converts this vector into 3 vectors that are called the query, the key, and the value. But these are just names. You get 3 vectors here, 3 vectors here, etc., all produced by the same mechanisms. You have weight sharing. In fact, it's even a linear networks in many cases, right? So far, no big deal. And then what you do is you take all possible dot products between the Q vectors and the query vectors and the key vectors. Okay, so dot products goes back to what I told you. It's attention. It's all about gain. I'm not drawing all the pairwise products between the neurons and then their sum to get the dot product, and then the n squared time. You have to repeat this operation n squared times. If let's say the sentence is long n, you have n queries, n keys. So you have to take n squared pairwise dot products, and each dot product is a little neural network, right? So you see immediately how this would become a mess if I were to draw everything. But basically you're taking, so here you have n square, this square block here represent 1 dot product. So you get n square of them. Then you apply a softmax per row, okay? And the softmax is what is used to gate the V's, so that the first output of the encoder mechanism, so that's the encoding, let's say, of the first word, is produced by a softmax applied to these weights here, to the V's, is a softmax combination of the V vectors, of the value vectors, where the softmax is produced by the attention, right? So that's how you impact this, this attention mechanism. Let's say that the first query and the first key are very similar to each other. Then they have a large dot product. They will have a large softmax. And then this V will be important, will be the important word, if you want, in order to calculate this hidden value here, as opposed to the other V's, right? So you begin to see how this connects to language processing. Now, the most important observation for us is that this architecture, very surprising, is invariant under permutation of the inputs. To see this, if I permute the inputs, you're going to permute the QKVs in the same way because of the weight sharing, right? So you're going to get the same permutation applied in this layer. Then you're going to get the same permutation applied to the dot products and to the softmax, and therefore into the outputs. So work this, for yourself slowly, but you will see very easily that this architecture is invariant under a permutation in the inputs. Now, this is a little bit strange for natural language processing because the input is not a set of words, it's a sequence of words. And in fact, what happens is that in the encoding of each one of the words, they add a few bits that are basically describing where is the word in the sentence. So the ordering is captured by a subset of the bits representing each one of the words rather than the sequence in the input. So maybe it's a little bit strange for language, but for physics, it's very good to have an architecture that doesn't depend on the order of the inputs for some problems, because very often you have, you have a set of jets. You don't have an ordering of the jets or 4 vectors or whatever you're looking at, right? So that's what I'm going to exploit in the physics applications. That's the same schema for the decoder part of one decoder module in the transformer. But okay, so application of physics, this is probably what interests you the most. These are examples of problems where we are applying transformers. So tagging extreme jets. So we have jets. We want to classify them in different prong classes, which are listed here, going towards fairly large numbers like 6, 8, etc. The input is represented by a list of towers. So each tower has the transverse momentum, the azimuthal angle, the pseudo rapidity. So 3 numbers, right? This is a variable length list. And one approach is to convert this into a high-level variable. So we can convert this into a vector of 16 high-level variables. We can combine it with the mass. So you could have a deep network that takes this 16 inputs plus the mass plus whatever else you want and try to do the classification into the prong classes. Or you can apply a different architecture, a recurrent architecture, or you can try to use transformers on this data, right? So that's what we do. We compare to the fully connected feed-forward network. We compare this to particle flow networks. We use transformers, and this is the kind of results that we are getting. You can see that the best results that we have obtained so far is with the transformers, about 91% correct. And the number of parameters is reasonable. Reasonable in the sense that these are big architectures with over 1 million parameters, but we can do better than a fully dense connected neural network that has 2 times or more the number of parameters. That's the first example. We have the confusion matrices, all those things, but that's details. That's the basic idea. I think you can see what it is. Another problem we're working on is the problem of jet parton matching for top quark decays. So here again, you have lists of jets that could include garbage jets, etc. And what you want is to reconstruct this type of events. So you want to identify the Qs, you want to identify the Bs, and there is a lot of permutation issues. First of all, the input is just a bag of jets, right? It's not a sequence of jets. Then you have invariance, permutation invariance between Q and Q, between the matter and antimatter, right? There is not a canonical distinction between the two. And then within a triplet, you can interchange the Qs, right? There is not a canonical way of distinguishes these 2 Qs. So you have all these invariances, and again, using transformer ideas to build architectures, you can address these permutation invariances in very nice ways. I'm skipping some of the details, but it's again equations about transformers. And just to show you some of the results. So here the baseline is provided by the chi-square methods, which is a method that basically look at all possible permutations and comes up with a score for each one of them. And again, using the transformers, the system we have, we call it spatter, probably not a very good name, but anyway, that's what we have. And you can see that it outperforms the chi-square methods in all cases fairly substantially, and it's also much faster. So it takes time to train spatter. It can take a few days, maybe a week in the worst case, depending on your hardware. But once it's trained, it's very fast. It can process an input in about 4 milliseconds, whereas the chi-square methods, which has to look at all possible permutation, takes considerably more time. I'll skip the application to neutrino, although Jianming is in the audience, so we can talk about that later. But this is an example to a completely different problem about neutron stars, where you basically have a basic theory, nuclear theory about these stars, and where you have a model that depends on, essentially in this case, on 2 parameters. There is different version, but let's say there is 2 parameters, 2 basic parameters. And when you expand the theory, what you get are curves in mass radius space on which the neutron star can live. So for different setting of these parameters, you're going to get different curves corresponding to different possibilities in the universe. And then, of course, from there, if you go in the forward direction, there are models that allow you to produce spectra from this radius. You first sample stars on this mass radius curve. Then you have to set some nuisance parameters such as distance, temperature, and dust. And then using the nuisance parameter and the mass and radius value, you can produce a spectrum, and then you can add Poisson noise to the spectrum, etc. Right? And of course, we're interested, long-term, we're interested in the reverse process, where you have a few very noisy observations about neutron star, and you would like to, go back and try to infer the values of the two parameters in the two-parameter theory, right? But I'm just going to describe the reverting this step, going from a mass radius curve back to the two parameters. So what you have, what is given to you is, let's say, 3 stars. You have 3 stars taken on a mass radius curve, and from the 3 stars, from the 3 masses and the 3 radii, you want to infer the parameters. Again, there is no natural ordering of the mass and the radii, right? So you're given 3 stars, the order does not matter. You want to infer the two parameters. Again, this is a very good problem for a transformer architecture that is invariant under permutation of the inputs. And that's sort of the prediction that we get. So you see the two parameters, M1 and M2. This is the EOS, means equation of state. And you have the predicted value versus the true value, and you see that it's pretty good. And this is only with 3 stars. As we add more star, we hope to be able to get more precise determination of those parameters. Here are some of my collaborators that have been instrumental on all this work. I'm not going to go through all of them, but of course you recognize Daniel Whiteson and Jiaming Bian, who have been working with me for many years now. This is Mike Fenton, who is a postdoc in Daniel's lab, with whom we're doing a lot of this this transformer-based work. This is Roman Verschainin, a mathematician, and Zikin Liu, who also have been working with me on some of the theory behind deep learning. And thank you very much, and I'll try to answer your questions.
Okay, thanks, Pierre. That was quite interesting. Since we're a lot of people, we use the hand raising mechanism. So first question up, I see Aaron. Go ahead.
Yes, so I'm a neutrino guy. I wonder if you can mention briefly the neutrino example that you gave. I'm so interested in that one.
The neutrino example here.
Yeah, okay, thanks.
So it's in the NOVA experiment. We have a different prong, and we want to classify the events in the outputs. Again, there is independence with respect to permutation. Oops, I don't have, actually, I don't have a slide of results. I cannot see the slide here. But basically, that's the problem where we apply transformer architectures. And again, it's all about invariance towards permutations. That's really what is useful for these kinds of physics applications. Anytime the order of things in the input do not matter, the transformer architecture is very well suited to handling that.
Okay, thanks.
So Pierre, there was a question in the chat that maybe you go back to the book again. Yeah, there's a question about your book.
Yeah.
So maybe just show that again. It's Deep Learning in Science, which is out or just about to come out. Yeah.
It's just about to come out. I mean, you can order it on Amazon or on Cambridge, but it's being printed. It's just distribution. So I think it will be out in June.
Okay. And next up, question.
Order it now. Sorry?
Next up, Kanishef. Go ahead.
Hey, yep. So I have a more practical question. So I have an experience with training transformers from natural language data, but never on like science data. And the thing that is very important, it seems, in the natural language is all these normalization layers, like linear normalization layers. And they have trainable parameters inside them. So like a batch normalization and stuff. So this stabilizes the training. So do you need this kind of normalization layers and normalization, batch normalization and stuff when you do these applications?
Yes, absolutely. I mean, you can try without, but we use it. Again, when I was describing the transformer architecture, I was really drilling down inside the attention module of the encoder. Outside of that attention module, you have normalization, etc. So yes, those are useful, and they essentially we use them.
Okay, gotcha. Yes.
The key thing to notice, though, is that in this transformer architecture, you have a lot of attention, but it's an expensive mechanism, because again, you're taking n by n dot products of vectors. So you can do it where n is reasonable, maybe in the tens, maybe up to 100 or so, but you cannot do it if you had an n that was very large, like in the millions. You could not take, 1,000,000 by 1,000,000 dot products, right? So it's all about, efficiency and whether you can do certain things in more compact ways or not, etc. Yes,
Chase, go ahead.
Hi, Pierre. Thanks for the interesting talk. I had a question about, for instance, you were discussing in the JET classification application, comparing the number of parameters, and you indicated that, for instance, you can reduce the number of parameters when using an attention module like this. But can you comment on, like, tangibly and quantitatively, what is it? What is the impact of having fewer parameters? Is there like a scientific reason why we care about that? Because from a physics perspective, I mean, once you have 1,000,000 parameters, you already have a lot of parameters compared to, what you might expect to be needed to model a system. So in light of things like, double descent phenomena and stuff like that, what is the difference between 1,000,000 and 3,000,000 parameters?
Well, it's both an easy and very difficult question. If you want to be precise, we don't have a good understanding anymore of these issues, right? This is an active area of research. People have noticed many times that neural networks can have way more parameters than training data, and still they don't seem to overfit, right? So there's a lot of research going on those issues. So if you want a quantitative answer, a precise mathematical answer, I think no one can give you such an answer today. I still think, the old thinking was that you should have more example than training parameters. I still think it's a good idea always to keep track of how many parameters you have and how much training data bits you have. And if you get into a regime where you have way more parameters than data, then you have to be careful about overfitting, because yes, maybe neural networks have a inherent tendency not to overfit, but you still want to be very careful about that. So you do cross-validation, you do the standard things to monitor as much as possible whether there is any kind of overfitting or not. But I cannot tell you, whether 3,000,000 parameters versus 2.5 is a fundamental difference or not. And we don't have a quantitative way, mathematical way of answering those questions.
Interesting. Thank you.
Rui?
Hi, yeah. Thank you very much for the very interesting talk. One of the nice features you mentioned for the transformer is that it's a permutive invariant. We know this idea set, which is also supposed to be invariant on the order of the inputs. Could you maybe comment on the difference or similarity between the both ideas, and how would one choose one over the other in different scenarios? Thanks.
It's not the first time that people have thought about sets and the need for an architecture that is invariant to permutation. And there is different ways of building architecture that are invariant to permutation. Transformer is not the only one. So there are other ways of doing it. And I don't have a prescription to tell you which one is the best one, or whether one approach is better than another one. Most likely it's problem dependent, right? But one advantage of transformers is that they come sort of as a box, right? They are very easy to deploy because they are part of the standard libraries. So they are convenient. That's a convenient solution. I will not tell you that it's the best or is the only one that gives you invariance with respect to permutation of the inputs.
Okay, interesting. Thanks.
Gilles, sorry for the pronunciation.
Yes, can you hear me?
Yes.
Yes.
Okay. Yeah, thank you for the very interesting talk. I was wondering if you had any recommendations for the initialization scheme for the query key and value layers.
I don't. I think
Right.
these are things you want to try.
I'd seen in some software repos that people were initializing the query and key with the same weights. I was just wondering if you'd heard about that before.
Yes, we have done that. And we have tried different initialization. There is. I would recommend, if you have a specific problem, that you try different initialization. Absolutely.
Okay, thank you.
Kunwar?
Okay, thank you for your interesting talk. And I want to know that if part of the data are symmetry, but another part of the data is the ordering is important. How could we do in this case?
Well, so you're saying, suppose you have data where a subset of the first 5 components can be permuted, and the last 5 the order matters, right? That's the kind of thing you're saying. Well, you would one way would be, an obvious way would be to have 2 separate networks that are processing the first part of the data that is permutation invariant, a second network that processes the remaining part. They both produce some kind of output, and then you combine those 2 outputs in a final network that produces the classification or regression or whatever you're trying to do. That would be an obvious way to do it.
Okay, thank you very much. And another question, and I want to know that if the data we fit is anti-symmetric, how could we do it? That exchange one pair, the result will go into a minus sign. How we do about this?
I haven't thought about it. I mean, if it's just is this just a regression problem?
Yes, a regression problem.
But are you saying if you permute 2 input, the output should change sign? Is that what you're saying?
Yes. Exchange the input. The result will go into a minus sign. Yeah.
Right. That's interesting. That's an interesting symmetry. I haven't thought about it, so. I haven't thought about it. I mean, one way, of course, you would train it. You give example both of the, of AB and BA with target +1 and -1. So in the training data, the anti-symmetry is reflected in the training data. That's the first thing.
Yes.
Favors these kind of things. I have to think about it.
Okay, and I think that there are some specific problems in the physics that we need to develop specific neural network to do with that.
if you want, send me an email. I'm going to think about it, and then maybe I can suggest a more specific solution for that. So send me an email. So I think it's an interesting question.
Okay, thank you.
Okay, any other questions or comments for Pierre? Blake.
Yes. Yeah, thank you for the wonderful talk. I just wanted to know, I'm relatively new to transformers or attention, but it seems to have had pretty significant impacts in a wide range of applications or revisiting tasks that you've had before with regression or I'm sorry, with recursion or convolutional networks. And so I was just curious if there's areas, other than maybe data that requires ordering, where it definitely wouldn't, you wouldn't see an improvement if you were to maybe revisit a task that you've done with a different type of network before.
I don't think there is. I don't have a general answer to the question. What I think is that there are, probably ways to use attention other than the transformer architecture, where it is both efficient and useful. For instance, if you had very large inputs, you couldn't use transformer because, again, it computes, n squared dot products. So what would you do? Could you leverage attention in those cases? But you ask in cases where attention does not help. I think it's almost impossible to answer such a question, right? Because how would you know that attention? Maybe you could say where attention has not helped so far, but it could be just because people didn't try it or didn't try it the right way. So you should really think about. I think if you're interested in these things, you should think in a more open way and just think, it's just the product of outputs of neurons. It's just this gating mechanism. How can I leverage this new mechanism on a given problem, right? And that's how you can design new attention architecture, I think, that haven't been explored yet.
Okay, thank you.
You're welcome.
Any other questions? We're approaching an hour. Going. Okay, thank you very much, Pierre. This was really, really interesting, and more soon. Thanks, everybody.
Thank you, everyone. Thank you very much.